Start it whenever you want to start it.
My hand's going to be in the way here.
That's okay.
Ready?
Yeah. I just want to show... Oh, nice.
Jeez.
Nice, Sue. That's your blooper right there.
In this episode of Nonsense Wars, we look at a fake 5292 motor from eBay. The quote-unquote buggy motor came in only a handful of sets between 2002 and 2006 and remains one of, if not the, most powerful Lego motor ever made. The combination of performance and rarity have made 5292 increasingly expensive. As of this writing, the average used price on Bricklink has risen to $86, undoubtedly contributing to the growing availability of fakes. But how does a fake compare to the real thing? I paid $17 for the cheapest fake I could find on eBay in order to find out. This motor actually shipped from the US, though it clearly came from a factory in China, judging from the markings and the English on the plastic packaging. The overall shape is nearly identical to that of the original, though it has much less aggressive Technic logos on it, and it forgoes the old 9-volt connector for an integrated PF lead. The pinholes on the body feel a little tighter than usual, but the PF connector feels basically just as good. What about the performance? Let's look at something simple first, the no-load RPM. We measured this using a standard regulator and the 32467 speed computer that we recently repaired. We tested both outputs. The outer ones provide less speed but more torque on both motors in both directions, but saying forward and reverse is entirely nominal. Quantitatively speaking, the two motors fell within 10% of each other, though subjectively the fake motor sounded like it surged a fair bit on the outer shaft. Okay, but the no-load RPM is more of a litmus test. Let's look at the power output. We can get this figure by measuring how quickly a motor moves a given load. To that end, we built jigs with masses attached to strings, attached to spools, with pulleys to keep the strings on the spools. The spools had a motor on one end and the speed computer on the other end. We would run the motors at full speed and catch the loads at the top of the travel so they didn't fall back down and mess up the reading. From the weight of the load and the radius of the spool, we can calculate the torque on the motor. From the speed computer, we can find the speed. Multiplying these two together gives the mechanical power. Note that you don't actually need the speed computer for this test. You could derive the angular velocity from timed runs with a stopwatch. We then tested this methodology by trying to replicate one of Philo's M-motor data points. We ran our motor under a similar load, crunched the numbers, and validated the result. At 9 volt, 4.4 newton centimeters, and 200 RPM, we got 0.93 watts, which is close to the 1.04 watts he got at 9 volts, 3.6 newton centimeters, and 275 RPM. Our figure seemed at least within the ballpark, and thus we tried the buggy motors. Here we ran into trouble. Philo tested his buggy motor with a 5.7 newton centimeter load, but ours, both the real and the fake, could not even pull half of that, and we eventually had to settle for just 1.6 newton centimeters. At this low load, the real buggy motor made 1.23 watts, and the fake buggy motor made 0.79. An appreciable difference, but unclear if caused by the motors or the setup given the circumstance. After more finagling, we suspected that a single regulator could not supply enough instantaneous power to start a heavily loaded buggy motor. It draws nearly 30 watts at stall, and a single regulator can output maybe 10 watts at max. The big brain move of running 2 regulators in parallel seemed to fix the problem and at least allowed us to lift much heavier loads. For our last tests, we pulled 4.4 Newton centimeters. Still, we ran into yet another hurdle. When lifting from table height, we got very inconsistent speed measurements, sometimes varying up to 50%. We determined that the motors needed more time to reach full power and moved our test bed up to the top of a ladder. Only then did we finally get mostly reasonable and consistent numbers from both buggy motors, and we used these figures for the final results. So how do we interpret these numbers? In terms of raw power, it looks like the fake motor does worse in general, but it may just have a different curve based on the different performance differences on the inner and outer outputs. That being said, I suspect that the fake has significantly worse efficiency due to its significantly worse performance in the single regulator power limited scenario. In both cases, we would need to record more data points or record more data, perhaps something for a future video. The real question to me is reliability, but unfortunately, we really don't have a good way to test that at the moment. So, on that note, this is the end of the episode, and have a nice day.
Okay, let's do the bigger gear. Can we fit a bigger gear?
Wouldn't the bigger gear make it harder?
Oh, yeah, okay.
Wait, no, it should be easier, okay. It's because, no, the ratchet popped off because it's not reinforced.
No, but that's also because the gear's spinning so fast that the ratchet's just flying off there.